The Airbus A380 is a super jumbo, the world's biggest passenger airliner. A pioneering marvel of the skies, it's packed with cutting-edge technology. Yet it owes its very existence to the most unlikely breakthroughs and inventions.
Wow! This is just glass.
These engineering connections range from a 19th century rocket to an ancient Mongol bow, and from the soaring genius of an eagle,
Look at that. There, you can see it.
to the humble bicycle pump.
What's all that got to do with the high-flying technology of the Airbus A380? We're about to find out.
Airbus 007 clear, takeoff 32 left, 290 degrees 8 knots.
This is the Airbus A380, also known as the Super Jumbo Jet. I'm setting out on a journey to uncover the A380's hidden links to brilliant ideas from across the world and throughout history. I'm about to reveal the engineering connections behind the biggest airliner the world has ever seen.
You can't help but just be stunned by the sheer size of the thing. It is the only aircraft where the passenger seats run the full length of the fuselage from front to back on both the lower and upper decks.
The cabins are 6.5 meters wide
It's the width of it.
and 50 meters long.
It is huge.
The A380 can carry up to 853 passengers, 35% more than its nearest competitor.
It's big. It's very big.
The wings are immense. 70 family cars could park on each one. But if the wings are too long, it can cause problems. It stands to reason that the world's biggest airliner is going to need the world's biggest wings. And they are absolutely huge. The total wingspan is almost the length of a football pitch. They have to provide enough lift to get 560 tons of people and machinery off the ground. But believe it or not, if these wings were built to a conventional design, they'd need to be even longer, and the A380 wouldn't fit into most of the world's airports. There's no good being able to fly if you've got nowhere to fly to. There are international restrictions on the maximum size of aircraft to avoid collisions as they taxi around airports. The absolute limit on wingspan is 80 meters. The A380's wings must be short enough to fit regulations, yet they must still create enough lift to get the world's biggest airliner into the air. The Airbus designers found a brilliant solution by drawing inspiration from the animal kingdom. But how did they do it? I'm about to take the first steps in my investigation. Aerospace engineer Dr. Peter Barrington thinks I should get a feel for how a conventional wing creates lift. And the best place to do that is in his wind tunnel at the University of Kingston in London. Peter's given me a handheld smoke generator so I can make the airflow visible.
So, Peter, how does it work and how can this help explain it?
Okay, well, basically the key thing to a wing is the cross-sectional shape. And that bends the air around the wing. The wing is able to make the flow go a lot faster on the top than it goes on the bottom.
The shape of the wing is designed so that air moves faster above than below. As a result, the air above the wing is at lower pressure than normal. So the higher pressure underneath the wing pushes upwards, creating lift for the whole aircraft.
You do get the sense that lift, flight, is just a function of that shape of the wing. That's all it can do.
The same smooth flow of air creates lift all the way along the wing. Or almost all the way. Peter's about to show me that conventional wings have a serious downside.
If you move a bit this way, see what happens as you come a bit closer to the end. A bit closer.
Out to the tip of the wing.
Exactly, yeah.
There it goes.
The airflow at the wing tip looks completely different. Instead of a clean, steady flow, there's a spiraling whirlpool of air. It's called a wingtip vortex. High-pressure air from underneath the wing is leaking around the wing tip and pushing down on the top surface.
That last 5% of the wing isn't really doing anything for you. It's not generating much lift.
The vortex means the wing tip doesn't provide any lift. So the wing is longer than is really necessary. And for the super jumbo jet, that's a supersized problem. This A380 prototype was launched through a curtain of illuminated smoke. The test showed that the world's biggest wings would suffer from huge vortices at the wingtips. To compensate for the loss of lift, the A380's wings would have to be made even longer. Too long to fit in with airport size regulations.
The Airbus designers had to find a way to clip their wings down to size. And it's a story that reveals the secret of soaring like a bird.
For the next stage of my investigation, I'm meeting another leading aerodynamics expert. But I hear he can be a bit difficult. His name is Cossack. And he's a steppe eagle, a species named after the wide-open plains of the Central Asian steppe.
I'll be honest, he's a big, impressive-looking thing.
Cossack is a scavenger by nature, and his lifestyle gives him a very similar problem to the A380.
He's gone.
To soar high above the plane in search of food, he needs a thermal, a rising column of warm air around 20 meters wide. But like the A380, his wings can't be too long, otherwise his turning circle will take him outside the thermal. So his wings are perfectly adapted for maximum lift with minimum length. And today he has agreed to take part in an unusual experiment. Oxford University zoologist Graham Taylor is going to show me exactly how Cossack deals with wingtip vortices by filming his wings in flight.
So these are little wireless video cameras.
So you can fit cameras to him.
Right, this is the tricky bit.
What do you do with that?
And I try and put this on his back.
Cossack's handlers help him into the Eagle Cam harness. And now he's ready for his close-up.
Okay.
Wow. With a bit of luck, what we're hoping for is that these cameras are pointing along the wings, aren't they?
That's right.
So we might actually see how they work and what they do. It's fantastic. Right.
It's blowing in the right direction for
There
good
it
flight.
goes. Yes. There you go. Yes, yeah, there's a beauty.
Cossack heads for the wide blue yonder, this time broadcasting on Eagle Cam.
There, you can see it. That was right along the wing. Is that what we're looking for?
That's what we're looking for.
Cossack can manipulate the feathers at the tips of his wings. To get maximum lift, he curls them upwards until they're almost vertical. This is the key to getting rid of wingtip vortices for highly efficient flight.
When it's actually soaring around in thermals, what you'll see then is that the wings are taking a heavy load the whole time. And as it does that, those wingtip feathers are curled up the whole way through that it's turning around.
It's disrupting this vortex that rolls around the end of the wing.
That's right.
Cossack's using his tip feathers to create what's called a winglet. This natural adaptation acts as a barrier against the vortex, blocking the path of air as it tries to flow around from underneath his wing. So he doesn't need long wings. His shorter, more efficient wings do the job. The question is, can engineers apply the same trick to these wings? And this 560-ton bird, the Airbus A380.
There's a hidden connection between the wings of the world's biggest airliner and the wings of an eagle. In wind tunnel tests, engineer Peter Barrington showed me how airliner wings suffer from spiraling vortices at the wingtips. Now we plan to solve the problem. This modification, inspired by an eagle's wingtip feathers, is called a winglet.
Okay, have a look at the airflow now.
As expected, the main body of the wing has a smooth airflow.
Maybe now we get to the tip.
But here at the wingtip, there used to be a spiraling vortex.
What do you see?
No vortex.
Now it's smooth. The vortex trying to curl around the wingtip finds its path blocked by the winglet.
So it's as simple as that. Basically, it's a barrier that stops the air getting round.
Exactly.
And as a result of that, we win back this stretch of wing.
Indeed.
The vortex has been forced away from the wingtip and up to the top of the winglet. So the entire surface of the original wing is now creating lift, effectively doing the same job as a longer wing.
That's what the eagle was doing.
Indeed. I mean, I think if we had as long as the eagle did to evolve, we could probably get this a little bit smaller.
Winglets can be made almost vertical to keep the total wingspan to an absolute minimum, just like an eagle's wings.
So it turns out eagles are really good at flying.
They are.
Yeah.
Extremely good.
The world's biggest airliner was saved by one of Mother Nature's innovations. But solving one problem creates another. Once the monster is in commercial service, how do you keep its running costs to a minimum? Because in the cutthroat airline business, every kilo counts. Extra weight causes the engines to burn precious extra fuel. So the A380 must be kept on a strict diet. And here on the final assembly line, I've got a unique chance to see its skin and bone.
Wow. We never normally see all this stuff because it's hidden behind carpets and internal walls and chairs and all the other comfy stuff we expect. But now to see the skeleton, the structure of the thing. And I'm struck by, well, I suppose the only other man-made thing this big odd being would be a building, and it would have thick stone walls. But here, without all the plastic stuff, you can see. It's got to be so tough. But it looks, I hate to say it, fragile.
Even the A380's outer skin must be as light as possible, especially since it covers a surface area of more than 3,000 square meters. So the challenge for the A380's engineers was to keep its weight to a minimum without making it too fragile. Finding out how they did it will take me centuries back in time, to the brilliant idea that connects the A380 with an ancient but deadly Mongol bow. But first, I've come to this abandoned Air Force base in the east of England to do my own testing of lightweight aerospace materials. Paul Hogg, a materials engineer from the University of London, will be my guide. He's bringing in the heavy artillery, along with some unusual ammunition. Chickens.
Very, very similar to the sort of test they use for aircraft engines and fan blades, basically.
Is it?
Yeah.
The aerospace industry uses chicken guns to simulate high-speed bird impacts at takeoff. It's a vital test of strength for the aircraft's outer skin. A punctured fuselage can cause the cabin to depressurize, asphyxiating the passengers. Or the bird impact could damage a wing, sending the aircraft out of control.
Any particular, I mean, how do we...
First?
I don't know. How do we select a chicken? That one?
That's the one, that's the one.
It's worth it.
This is going to be very messy, isn't it?
I hadn't thought of that. Yes, it is. The chicken is loaded.
Paul sets the chicken gun to fire at a typical A380 takeoff speed. This will be a 290 km/h collision.
Connect my... That is now live.
But which will survive? The chicken or the aluminium?
5, 4, 3, 2, 1. Well, it was worse for the chicken. I'm amazed.
It's deformed a fair bit, but it's certainly kept itself together very well.
There's a dent, but no catastrophic puncture. But on the world's biggest airliner, saving weight is an absolute necessity. So what if we test thinner aluminium at just 0.9 millimeters thick?
This is to save weight. So if we decided that the heavy stuff we used was too much weight, this is what we got.
That's the sort of thing you do, yeah.
Right up, let's see what happens.
But will it survive?
Whoa! Look, that, straight through. Ooh. Just remind me, this, we haven't used like baking foil or something here. This is...
That's the real thing.
What's given way? Why has it done that? Why can't it withstand that?
Well, it's really just down to the thickness. It's only got a certain amount of give in it. And when you've got a thinner material, then you're really sort of stretching the limits of what it can do. A big hole. Not a good thing in an aircraft fuselage.
The thinner aluminium is stiff enough to make an aircraft's outer skin, but it isn't strong enough to withstand high-speed impacts. It bends, then tears completely like a sheet of paper. No aircraft could risk such a catastrophe on a flight loaded with passengers. But the Airbus designers found a way to make aluminium thin and at the same time incredibly strong. And that's where the Mongol bow comes in. In the 12th century, the Mongol Emperor Genghis Khan set his sights on world domination, and he planned to destroy his enemies with archery. This is the longbow, an extremely powerful weapon constructed from a single piece of wood. The wood must be strong enough to survive the heavy bending force of a man's body weight. But to conquer the world, Genghis Khan needed a bow that could be fired from horseback, by mounted warriors in a highly mobile army. I'm about to find out why that was a problem with traditional bowyer Steve Ralphs.
I can see how the principle, the theory works, because, you know, horse, mobile, weapon, great. But practically, how did it actually work? How could I kill somebody with this, sitting on this?
The first shot is here as you come in from the left-hand side of the horse. So it's 1, 2, 3, up and over, 4.
So let me just try those. So, sorry.
If there's one thing I need, it's a compact weapon.
My arm's twisted now, I can't.
And I can vouch for the fact that the longbow is not it.
So the problem with the longbow for this job is its longness.
So what happens if you try to make a shorter bow with the same power from a single piece of wood?
So I'll give you a short bow.
Thank you.
And some protective equipment.
Right. Yeah, that's not worked at all, has it?
Here's why. When a bow is drawn, the outside stretches so that it's longer than before. But the inside squeezes, making it shorter than before. So the bow has to handle two very different forces at the same time. With a shorter bow, the bending is much greater and the wood just isn't strong enough. So the Mongols came up with a brilliant idea. If there are two different forces, use two different materials.
This is horn, it's buffalo horn, sort of thing they would have used. pieces of this, which is, I mean, it's very tough. It doesn't mind being squashed. It can cope with that very well. And then on the outside of that is a layer of sinew, like this, which is happy being stretched. And in fact, I can break it down a bit and we can...
The sinew comes from tendons in a deer's hind legs, and its fibres are highly elastic. The combined properties of horn and sinew make for one ideal weapon.
You actually bind sinew to this side of the bow, the back of the bow. You place horn plates on the inside of the bow, on the belly. And then you can, in a very short bow, you get the same drawing.
Now, if you did that with just a wooden one like the one I just did...
Well, you saw the results.
Yeah, but this, you can draw and it can take a bigger curve. Wow, you can feel it.
With buffalo horn on the inside and sinew on the outside, the bow can handle squeezing and stretching at the same time.
It's like elastic.
Mongol bows were short enough to fire from horseback, but still strong enough to hit targets 300 meters away. The Mongols developed not just a great weapon, but a great concept, the composite. Take two materials with useful properties and put them together to make something far better.
As Genghis Khan might have said, it was easy, once you knew how.
Fast forward to the 21st century. These sections of the A380's outer skin are made from a composite of two materials. Like the buffalo horn in the Mongol bow, lightweight aluminium provides stiffness. But with a heavy impact, it will bend, then rupture completely. It needs a second material, like the sinew in the Mongol bow, to give it added strength. And Paul Hogg has given me an amazing suggestion. Glass.
Well, it broke, obviously, but just tell me, I mean, I knew it would break, but tell me why it broke and how it broke.
Well, basically, it's a brittle material, so it was deformed, cracks just propagated, some of them propagated all the way out, you can see the other ones are formed here. End of the story.
An ordinary sheet of glass
It feels flimsy to me. It's also scarily light.
A short bow made from a single material will bend, then break. The composite bow survives. An aircraft skin made from a single material bends, then ruptures. Can the composite skin withstand the impact?
Okay, I've come down to the business end of our little chicken firing range here because I really want to see what happens when the chicken hits the glare. Does it bend? Does it come back? I want to see how it behaves.
You ready, Richard?
Yeah, I think so. You're
Okay.
on time.
3, 2, 1.
Oh, well, it's not very nice being that close to a very fast chicken, but it's resisted it. It hasn't gone through.
There's a dent, but the glare survives.
It does work. The two materials working together are better than either alone.
That's fantastic, isn't
Yeah.
it?
But could glare even stand up to terrorist attack, like these bomb explosions? In tests, the Federal Aviation Administration placed plastic explosive in a luggage container made of glare. This was the result. A box whose strength comes from glass. For the A380's designers, glare is the perfect combination of high strength and low weight, vital for an airliner this size. Glare forms 470 square meters of the A380's outer skin. It's 25% lighter than aluminium, one reason why the world's biggest airliner has better fuel consumption per passenger than a family car. And thanks to composites, an idea inspired by the Mongol bow, it's tough enough for the rigors of flight, even with a novice pilot.
So Richard, if you want to take control of the airplane now, if you get your hand on the stick ready to take over.
Really?
Yep.
Right.
Go for it. If you put full stick to the right now.
Whoa!
There you go.
Whoa!
That's it.
It feels as light as a feather.
Are we doing aerobatics in the world's largest airline?
When it's in the air, the A380's enormous size is not a problem. But in the next stage of my investigation, I plan to find out why size is a big issue when the A380 is still on the tarmac. This is Airbus headquarters in Toulouse in southwestern France. A nest for breeding the world's biggest birds.
Whoa! This place is unbelievable. Everything in it is vast.
The final assembly line is nearly half a kilometre long and 50 metres high.
Apparently this building is so enormous that, rumour has it, it can form its own clouds up near the ceiling.
On this scale, human beings seem tiny and insignificant. The fully assembled A380 is by far the longest, widest and tallest airliner in history. The upper exits stand nearly 8 metres off the ground. And that's where the problem comes in. If there's an emergency, the passengers have a long way to go to escape and survive. This is an evacuation test of the A380. To satisfy international regulations, all 853 passengers must evacuate, using only half of the plane's 16 exits. They have just 90 seconds, the estimated survival time in the event of fire. To save their lives, passengers need an escape route fast. They're trapped at the height of a 3-story building with nowhere to go. As a result, the A380 has the biggest evacuation slides in the world. But regulations require the slides inflate in just 6 seconds, so that the first passengers to arrive at the doors don't block the exits. The only way to do it is to make a surprising connection between a life-saving slide and a device that was designed to kill. To prove it, I'm going to build and test my own model of an evacuation slide. My airbag is 50 metres long. Even so, it would take nearly 8 of these to make the same volume as an A380 slide. So maybe inflating it won't be too difficult.
This is a very big bag, which basically is what an evacuation slide is. And when it comes to inflating a bag as quickly as possible, well, there is an obvious way to do it.
It should be as simple as blowing up party balloons. Attach the bag to a cylinder of compressed gas and inflate for exactly 6 seconds as per regulations.
Right, are we ready? 3, 2, 1.
It is inflating.
5, 6.
The trouble is, it's nowhere near fast enough. After 6 seconds, the bag is still much too soft to take the weight of desperately fleeing passengers. So the A380's designers unleashed their secret weapon: rocket power. I'm using 19th century rockets because the primitive design makes it easy to see the key ingredient: gunpowder. These rockets weren't very accurate in their day, but they did create lots of gas, exactly what we need to fill the bag. All I have to do is make sure the rocket can't move.
And here it is. One rocket fits onto this bed at the back, down this pipe leading to the bag. Obviously the rocket is facing this way because I want the exhaust gases going into the bag, not the actual rocket. So, fix it down. I need a light.
This time, I'm using the rocket gas as a booster and combining it with the compressed gas. But will that be enough to fill the bag in the critical 6 seconds? Nice job on the first half of the bag. Not so good on the second. And for an evacuation slide, anything less than full inflation would cost lives.
Well, the rocket gave us more speed, definitely, but we still didn't fill the bag. We need to get more air in. And to do that, the Airbus designers used one of these.
It's called an aspirator, but it's basically just a funnel. As the funnel gets narrower, the rocket gas moving through it speeds up, causing the pressure to drop. That should create a vacuum effect, sucking in extra air from the surroundings to inflate the slide. But will it be enough to transform a weapon into a lifesaver? It's a stunning success, easily inflating in 6 seconds. 2/3 of the gas filling the bag is fresh air, sucked in by the aspirator. And that's how you rescue people with rocket power.
I mean, it works. Clearly, it works. It might have been pretty useless as a weapon of war, but turns out it can save lives.
With this device, the A380's slides inflate in 4 seconds, 2 whole seconds inside the required time. In the emergency drill, all 853 passengers evacuated in 78 seconds, easily beating the 90-second limit. Thanks to rocket-powered slides, the A380 was officially certified to fly. But the designers hope they'll never be used in a real emergency.
Needless to say, if you're an engineer, it's better to ensure that an emergency never happens in the first place.
On any given flight of the A380, one moment above all is fraught with danger. Touchdown, the earth-shattering collision of wheels and tarmac. The world's biggest airliner weighs 560 tons, almost as much as 200 family cars. But a single piece of life-saving technology must bring all 853 people gently to Earth. I'm about to find out what it is by landing the world's biggest airliner myself at New York's John F. Kennedy Airport.
This is not a normal approach to New York.
I'm with pilot Peter Chandler in the A380's state-of-the-art flight simulator. It rocks and rolls on huge hydraulics, making the effect in the cockpit highly realistic.
It's so convincing. Heart's going.
If you're ready,
Yes.
you probably ought to take control.
Yes, right.
And I'll sort out the configuration of the airplane.
Right.
That's the landing gear going down.
So they're now hanging in the breeze, which, you know, would...
Yeah.
For you
Just
and me,
concentrate on following the green cross. So you need to pull the nose up a bit.
Sorry.
Peter's controlling the engines and the A380's airspeed, giving me less to think about. But I must still use the joystick to keep the plane level and straight before the final approach.
Yeah, you're a bit to the right, actually, so you want to come to the left a bit.
Oh, right. Oh, right.
That's it.
A normal soft landing requires an incredibly slow rate of descent. Just 1 meter per second, slower than walking speed.
Back on the stick a bit.
190. Sink rate. Sink rate.
Oh, what does that mean?
No, that's it.
Retard.
That's it.
Retard. Retard.
Good. Well done. Okay, I have control.
My landing was at double the normal speed, so the simulator gave me a very heavy jolt.
I'm actually bathed in a fine layer of sweat.
In real life, this impact would be easily absorbed by the A380's landing gear. Each set of wheels is cushioned by a giant shock absorber, the crucial technology for bringing passengers safely to Earth. Witness this notorious incident at Hong Kong's Kai Tak Airport in 1993. A Boeing 747 gets caught in a heavy crosswind while approaching the runway. As the jumbo jet twists in the wind, a single set of landing gear sustains the entire impact. But it's strong enough to survive. The A380's landing gear is rated to handle such extreme.
The 747 is sitting on the runway for 4 hours before finally leaving at 8:20 p.m. Minutes later, other pilots contact air traffic control with horrible news.
We just saw an explosion out here, 5507. In a good position. We just had looked like an explosion out there, about 5 miles away, 6 miles away. We just saw an explosion there. It was about 16,000 feet or something like that. It just went down.
The tragedy was witnessed all along the Long Island shore. An aircraft turned into a fireball that leaves a burning mystery. "12 minutes after leaving New York, a passenger jet explodes over the Atlantic.
What you see in the water down there is what's left of that TWA flight that was bound for Paris from JFK. It is the burning wreckage from that plane.
Turned on the TV and it was pretty horrific. Flames all over the ocean. I learned quickly it was a 747, so I knew automatically we had hundreds of dead people on our hands. I wasn't looking forward to going up there at all.
Bob Benson and the NTSB team rush to the scene, but rumors get there first.
People were talking lightning strikes, people were talking meteorite strikes. People were saying, well, maybe a cell phone on board caused the explosion. We had a lot of things we had to eliminate pretty quickly to kind of calm things down.
All they know is the death toll. 230 people on board, and no survivors. The only good news, the wreckage lies just 100 feet deep, making the flight recorders easier to find. 7 days later, they raise the boxes and hopes for an early breakthrough.
I was in the hotel. It was probably 8 o'clock in the evening. I got the call, and I expected the recorders to be quite damaged and perhaps hard to recognize, but they weren't. They were virtually intact, and we were very, very happy to see them.
But the boxes record a normal flight to 13,000 feet. Then they just stop dead.
When I realized that the recorders were not going to help us out that much, I knew we were in for a long haul.
They have only one way to solve the mystery: retrieve the wreckage scattered from miles along the seabed. Week after week, salvagers bring up piece after piece.
We ended up recovering 95% of the airplane, which was quite remarkable for the time, and it became very important that we get up every single speck of material we could off the bottom.
A hangar on Long Island holds a jigsaw puzzle with 1 million pieces. Painstakingly, investigators start to reassemble the fuselage.
When you put it into 3 dimensions, you can tell what went wrong first, what went wrong 1 instant later, 1 instant later, 1 instant later, and ended up in the destruction of the airplane.
After 4 months of careful reconstruction, a pattern begins to emerge on the reassembled plane. NTSB metallurgist Jim Wildey.
We were able to look at the fracture patterns in all these pieces right here to a position just in front of the wing front spar. And we could see how the front member of the fuel tank was pushed forward into the backside of the front spar. From this, we determined that the breakup of the airplane began here in the wing center section fuel tank.
Investigators recall a similar accident a few years before. The center wing fuel tank exploded as this 737 sat on the tarmac in Manila. But why? Aviation fuel is designed to be much less flammable than ordinary fuel. And the records for both planes show both of the fatal fuel tanks were nearly empty. Flying with an empty tank isn't unusual. A 747 carries over 50,000 gallons of fuel, twice what it needs to cross the Atlantic. But an empty tank contains something, air, and air contains oxygen. If heated, any fuel left in the tank turns to vapor. Mixing fuel vapor with oxygen is a formula for an explosion. As both planes sat on the runways, something must have heated the tanks.
Underneath the wing center section are air conditioning units. These units operate off of bleed air from the engines and provide cool air to the passengers. These units also generate a lot of heat that comes up into the wing center section fuel tank and increase the flammability of the fuel-air vapor mixture inside the tank.
Could a fuel tank explosion bring down a plane? They test a model. Catastrophic, yes. But what could ignite the explosion? The NTSB's Bob Swaim has a theory.
I kept coming down to the point where I couldn't avoid, and I almost had to say over and over, that it had to be electrically related.
Inch by inch, Swaim examines miles of wiring.
We had cracks in the insulation where the copper was exposed and we could have short circuits. We learned quickly that the condition of the wiring was pretty sad in that airplane.
The final piece of the jigsaw, the wires leading to the fuel sensor inside the center wing fuel tank, are chafed.
Once the copper is exposed, anything that's conductive could give you a bridge between two wires.
It would have been like putting a spark plug into a highly flammable atmosphere and having that spark plug fire time and time and time again.
Thousands of aircraft with empty fuel tanks fly every day. How to prevent another tragedy? To find out why TWA 800 exploded, investigators reconstruct the wreckage. They find that a spark in an empty fuel tank brought down the plane. How do you make a tank explosion-proof after most of the fuel is burned? Reduce the level of oxygen. It's called inerting. Inerting works by replacing the flammable oxygen in an enclosed space with a safe, non-flammable gas. But inerting systems are big and costly. Scientists at the FAA's Tech Center in Atlantic City get a tall order. Develop an inerting system light enough and cheap enough for a fuel tank.
It was a very challenging assignment. We were asked to do something that hadn't been done before.
After 4 years' research, Gus Sarkos and his team developed the answer. Separate the air molecules.
The heart of the fuel tank inerting system are the air separation modules. Each one of these modules contains hundreds of thousands of these small hollow fibers. These fibers allow air to pass through them and separate the oxygen from nitrogen in the air.
It works by feeding pressurized air from the engine into the hollow fiber membrane. Air is about 20% oxygen and 80% nitrogen. The oxygen molecules are too large to pass through. Only the smaller, non-flammable nitrogen molecules can. They're forced along the membrane and then piped into the empty fuel tank. Ignition impossible. In 2006, a decade after the tragedy, fuel inerting becomes law. All new planes are now automatically fitted with the system. Boeing is also retrofitting all 737s and 747s at a cost of $1 billion. December 20th, 1995. American Airlines 965 departs Miami for Colombia. On board, 163 passengers, many on Christmas vacation. At 9:41 p.m., Cali Air Traffic Control loses contact with the flight. At Cali Airport, anxious relatives wait for news. The plane never arrives. The next day, the missing 757 is located 10 miles off course, high in the mountains east of Cali. Just 4 survive.
He perdido también a mi esposa y a mi hijo. Para poder brindarles esta entrevista, ha sido el milagro que se ha realizado.
Investigator Steve Corey arrives in Colombia the next day.
It was characterized by a pretty steep slope and a lot of jungle and trees, and it had rained an awful lot. To recover the bodies and remains was very, very difficult and hampered because of the conditions on scene.
Corey's team locates the plane's black box and the reason it strayed off course. 9:26. American Airlines 965 requests descent clearance. Miscommunication with air traffic control leads to wrong data entering the flight management system. 937. The plane turns away from Cali in a wide semicircle, heading east into the mountains. 941. The crew now realize they are on the wrong course, but are just seconds away from hitting the mountain. Such crashes are classified as controlled flight into terrain, or CFIT. The investigation soon determines this isn't a structural failure.
There was nothing wrong with this airplane, and yet it flew into the ground. A perfectly good airplane flies into the ground.
AA-965 is just the latest victim of controlled flight into terrain. In the 1960s, commercial flight soared, and so did CFIT accidents. Most were caused by pilots disoriented in bad visibility. They had no system to warn them they were about to crash.
Deep landing, deep landing.
Aviation engineer Don Bateman takes up the challenge. For 40 years, he's worked to make flying safer, ever since a CFIT accident hit close to home.
I was always interested personally because I'd had a couple of colleagues from Boeing who had flown an airplane into a mountain.
Bateman starts with technology developed in World War II. The radar altimeter gives pilots a vital piece of data, their height above the ground. It proved a lifesaver for bomber crews landing at night, often in bad weather. Using old technology, Bateman starts work on a new breakthrough. In 1970, he produces the world's first ground proximity warning system, GPWS. Bateman's system constantly measures altitude, then feeds the data to a computer. The computer compares the plane's altitude to its speed and rate of descent. If the plane descends too fast or the terrain suddenly changes, GPWS issues a warning to pull up. Boeing is the first manufacturer to install GPWS on all new aircraft. In 1974, the FAA made the system mandatory on all large aircraft.
The result was about almost a magnitude drop in the frequency of these kind of mishaps.
By 1995, all U.S. planes had been flying with GPWS for years. So why didn't it save Flight 965? American Airlines Flight 965 flies into a mountain in Colombia, despite an alert from the ground proximity warning system.
They actually got a warning from the ground proximity warning system, as I recall, something like 15 seconds or so.
And they reacted properly to that warning by pulling up the airplane, increasing power to max power and so forth to try to recover or climb the airplane.
It was not enough. There wasn't enough warning.
Just 100 more feet would have saved them. The crash shows the blind spot in GPWS. It only looks down, not forward. If the terrain ahead suddenly rises, GPWS can't warn the pilot in time. The system's inventor had spent years working on a solution. But to read the landscape ahead, Don Bateman needed global maps with unprecedented detail, maps that didn't exist. Or so he thought.
The Soviets had been making terrain charts since about 1923. Even during World War II, they were doing this. And they were collecting data from all over the world. At the end of the Cold War, suddenly they began to sell this data. That unlocked some things I never even thought about. And so I talked my company into buying as much as we could.
Bateman not only gets the terrain maps, he gets technology that can pinpoint a plane's position. The technology is another spin-off from the Cold War. In 1983, Korean Airlines 007 flew off course over Soviet airspace. It was shot down, killing 269 people. The incident convinces President Reagan to declassify a military navigation aid called the Global Positioning System, GPS. Finally, Bateman has all the pieces to save lives. Enhanced GPWS still uses a radar altimeter to read the ground below. Onboard GPS uses satellites to track the aircraft's exact position. Combining the position with the terrain data shows the pilot what's ahead and warns him if the aircraft is flying into danger.
Terrain ahead. Terrain ahead. Terrain ahead.
Here it is in action over Arizona. The screen displays the surrounding terrain. Red represents ground higher than the aircraft. In bad visibility, the pilot may not know he's on a collision course with the mountain. The display warns him. If he ignores the screen,
Terrain ahead. Terrain ahead. Terrain ahead. Terrain ahead. Terrain ahead. Terrain ahead.
Stay right.
Bateman was perfecting this system when Flight 965 crashed.
Suddenly, when Cali happened, and great interest started then to perhaps, because we could get, instead of 15 seconds with a warning, we could give like a minute of warning. A minute is a long time for an airplane.
Terrain ahead. Terrain ahead.
All U.S. registered aircraft that carry at least 6 passengers must also carry EGPWS.
We have not had another control flight into terrain accident on aircraft with this technology on board. It is a great technology. It is an effective technology. And 95% of the airliners in the world have it today.
Now in development, the next generation. A clear 3D view of the terrain, no matter the time or weather. Pilots won't even need to look out the window. It's all on the screen. July 25th, 2000. Charles de Gaulle Airport, Paris. An Air France Concorde prepares to take off to New York. The world's fastest plane is the ultimate in travel with a perfect safety record. 100 German tourists are beginning the holiday of a lifetime. Instead, disaster. A passenger in a truck captures these pictures. Seconds later, Flight 4590 crashes into the side of a hotel. Killing everyone on board. A Concorde, the plane with one of the best safety records in the world, crashes on takeoff. No survivors. 100 passengers and 9 crew are killed. 4 people die on the ground.
People were walking around in a complete state of shock and disbelief that this dreadful event had happened.
French investigators move into action. They are joined by their British counterparts. Much of the plane was destroyed by fire, but the black boxes are recovered, and they reveal what happened. The fire breaks out as the plane lifts off. The crew shuts down one engine, thinking it's on fire. Then they can't retract the undercarriage. When another engine backfires, control becomes impossible. 72 seconds after liftoff, Concorde crashes into a hotel. The fire triggered the disaster, but what triggered the fire? Investigators learn a lot from pictures of the final moments.
You could see inboard of the engines around the undercarriage bay that the flames were emanating from there. They might have been emanating from the engine as well, for all we knew, but certainly it wasn't just an engine fire.
Investigators pinpoint the source of the fire, a leak from a fuel tank close to the undercarriage. What caused the leak? Scattered along the runway, they find debris from the plane, including 2 sections of tire, each weighing around 10 pounds. It suggests a blowout.
The 2 large pieces of tyre that were found there, when they were brought together, they fitted together very neatly, as though they'd been cut through.
There is a second clue. A piece of metal debris matches the cut in the tire. It fell from another plane that took off minutes earlier.
The piece of metal which we believe caused the tire burst was a strip of titanium about 1 foot long, inch wide. It was L-shaped, so that as the tire approached it, it was inevitably going to cut the tire rather than to flatten the piece.
How could a burst tire cause such a disaster? Investigators find a third clue. A small section of fuel tank. With these 3 pieces of evidence, they construct the chain of events.
When the tyre burst, a great lump of rubber was carved off this tyre. Some of the rubber hit electrical wiring for the brake fans. Another 10-pound lump of rubber was carved off this tyre here. It went slamming up there by tank number 5, causing the fuel to burst out of the tank. And that fuel came cascading out of that tank, came in contact with the arcing electrical wiring, and that was what caused the fire to start.
How to ensure it never happens again? Concorde designers craft a plan to strengthen the fuel tanks using one of the toughest man-made substances in existence. Kevlar is a material used to line bulletproof vests. Pound for pound, Kevlar is 5 times stronger than steel. Mats woven with Kevlar are fitted inside the tank. If the tank is penetrated, the Kevlar mats are designed to plug the hole. They would reduce a fuel leak by 95%. Part 2 of the solution, a tougher tire. Aircraft tires are unique. They must be able to support 185 tons at speeds in excess of 250 miles an hour.